Hello everyone, my name is Jake Jensen. This is for Organic Chemistry, week 15. This is for the assignment to solve a combined spectral problem, and I am part of group 4. So to start out, first of all, I guess I have to apologize for my allergies. Hopefully you can hear me okay. I'm also recording with my phone, so hopefully this turns out good. So we'll start out with our IR spectrography here. I kind of have some notes on here so I remember what to talk about, but on first glance, you can clearly see an OH group here with this wide, broad frequency downfield here on the spectrum. It's kind of suspected with how many oxygens we have there that there would be some sort of OH group. With that oxygen, we also see a carbon double bond with an oxygen here, and some more carbon oxygen down here. Probably, I would suspect at this point, linked kind of to this OH group. We'll see as we go along, but that's my first thoughts here. We'll go to the last page here and we will fill that out. So we have, let's hold those up side by side. Okay, around 3,400 to 2,400 with that broad stretch. 3,400 is when it starts, that OH group that we suspect. Around 1750 for that carbon double bond oxygen, and 1,200 to 1,400 for that carbon single bond with the oxygen. Moving on to our 13 carbon spectra here. These ones I'm not quite as good at, but luckily they're a little easier to tell where they are. Right around 180 we have a shift, and about 35 and 20. These are typically sp3 carbons. This one would probably be more shielded than this one from that frequency. Upon research, this is probably a carbonyl carbon here. So we'll go back to our last page and fill that out. So 13 prime carbon. Sorry. I figured taking these sticky notes off would be a little bit easier than it is. So we can fill that out. Like I wrote here, this is probably near withdrawing group, and this sp3 carbon is probably more shielded, we would suspect. So moving on to our last spectra here we can look at is our H1 NMR. These are kind of hard to tell with this printout, but it appears to have a triplet here at about 2.5, and right around 2 it appears we have a quartet. So coming back over here, we can fill that out as well. They gave us the integration, which helps a lot. So it appears as if the CH2 group have equals or symmetry, perhaps, with that 2.5 shift. Up here we have our molecular formula to refer to. Degrees of unsaturation, we have our formula here, tailored to organic chemistry, that is. So we've got 2 times the amount of carbons, plus 2, plus any nitrogens we have, which we do not have any. We know that, and subtract the amount of hydrogens, divide all that by 2. So here we have 2 times 5, which would be 10, plus 2, so we're up to 12. No nitrogens like I mentioned. So 12 minus 8 would be 4, divide that by 2, and we have 2 degrees of unsaturation. This took me a long time. Hopefully I got this right. Lots of trial and error. These are a lot easier on the homework than when you're actually given everything blank. I believe this is what we've got working with us. We have our 2 carbons here that, let's see, right here, 2 CH2 groups that appear in symmetry, equal here. We have our sp3 carbon that is more shielded. We have our OH groups that we suspected up here. Carbon double bond with oxygen and carbon single bond oxygen right here. This is what I suspect would be the proposed structure. Hopefully that's right. As you can see, I wrote down a lot. This is the best I could come up with. So we do match with the amount of carbons, hydrogens, and oxygen, degrees of unsaturation. All the spectra lead to, or point to this proposed structure. So yeah.